Welcome everybody. This is our 23rd seminar in the series. And today we have Gianni Arioli, who's gonna tell us about Navier-Stokes equations, but I'm very excited to hear about it. I really like this topic. Gianni did his PhD in 1996 in Milano, I think at the University of Milan.
Yes.
And then he went for a postdoc in Stockholm and then returned to Italy, to the Università del Piemonte Orientale. And then after a few years, he moved to Politecnico di Milano, where he is now a full professor in mathematical analysis. And in the past decade, Gianni has made a lot of contributions to the field of computer-assisted proofs in a lot of different dynamical systems and nonlinear PDEs, often in collaboration with Hans Koch. They're really a special duo in this field. I would say very exceptionally strong. Well, today he's gonna symmetry breaking is in fact one of their main topics, I think, in the past years. And today he's also gonna touch on that and bifurcations. And for well, complicated equation, I guess, the Navier-Stokes equation. So Gianni, the floor is yours.
Thank you very much. Thank you for the introduction as well. So not to change anything, this is also joint work with Hans Koch. And in fact, the first part is also joint work with Filippo Gazzola, also from my department. So we're going to talk about Navier-Stokes equations. So these are the equations that you all know. We're going to discuss this equation in the square because we want to make the problem as simple as possible. And since we don't like, well, we want to discuss bifurcations, so we need a parameter. The parameter is going to be the viscosity nu, but since we don't like the parameter in front of the Laplacian, we just set gamma equal to nu to the -2. We rescale u and we get the equation that you see in the middle. Can you see the pointer?
Yes.
Okay. So, and we get this equation here. Alpha, the value of alpha, of course, well, would be just 1 over nu, but it doesn't really matter because, of course, this is the coefficient in front of the derivative with respect to time. So we can set it however we want just by rescaling time, which is what we are going to do. In fact, when we are looking for periodic solution, we are going to look for 2π periodic solution, which simply means that we are considering solutions of period 2π over alpha. If we get rid of alpha, we just have solutions of period 2π over alpha. So this is a parameter that will enter when we will discuss 2π periodic, when we discuss periodic solutions. So I'm going to talk about two different results that we obtain. One concerns stationary solution, the other one Hopf bifurcation, therefore periodic solutions. In any case, we are going to consider Navier boundary conditions, which can be also called slip conditions. And this amount to having the flow just flow around the boundary of the box, the boundary of the square, without any friction. So in short, this Navier condition simply means that the velocity u is parallel to the boundary, and the actual conditions are written explicitly at the bottom of the slide. So now the parameter that we are going to consider will be gamma. So gamma is just the inverse of the viscosity, more precisely the inverse of the square of the viscosity. Now we're going to consider a forcing F, which is symmetric with respect to a reflection about the horizontal middle line. So the line y equal to pi over 2. Yes, the square, I forgot to mention, the square is 0π squared. So the side, the length of the side is 0π for obvious reasons. And we're going to consider a function f which has this symmetry. So this simply means that it is symmetric. Well, this is a fluid, it is symmetric with respect to the line. And given the symmetry of the whole domain and the symmetry of the line, we expect that a solution exists which respects the same exact symmetry. This is the case for the stationary solution, but of course one expects the same also for time-dependent solutions. So we have the pressure P and the velocity with components U1 and U2. In fact, concerning both cases, but in particular concerning stationary cases, we are considering the function f, which has only the first component different from 0, And well, I could give you the explicit definition of the function f, but what really matters is that, well, it is a Fourier polynomial concentrated in the center of the square. So this is the approximate graph of the function f. It is actually a Fourier polynomial of degree 11. So this means 11 times 11 coefficients. So what is the purpose of this particular function? Of course, this is completely arbitrary, but the idea we had in mind was to study what happens if you have some sort of propeller in the middle of the square that pushes the fluid, in this case, to the left. So this is the reason why we chose this particular shape. And of course, you can think that instead of having the parameter gamma that I mentioned, we have a parameter in front of f. It's just a question of what is scaled with respect to what. And then the idea is to see what happens if, for example, the force or the speed of rotation of the propeller changes, and see if some bifurcations happens when we change this force. Anyway, the reason for this particular shape is just think that we are pushing the flow in the middle and see what's happened. Now, this is our main result concerning the stationary case. In fact, we actually have different results which are proved by pen and paper, but since this is a seminar for with computer-assisted proofs, I will only discuss the computer-assisted parts. Actually, I will mention one result which is a pen and paper result, but I will focus on the computer-assisted results. So this is what we observe. We have the viscosity decrease from, yes?
Just a quick question. So the function f, to be clear, it is not depending on time. It's just spatial.
No,
right?
no, it's constant. It's constant.
Yeah.
I'm talking about stationary case. So yeah, but even in the Hopf bifurcation, it would be a constant function. Yes.
Yeah. Okay. Thank you.
So for now, I'm talking about stationary. There is no time whatsoever. And now what one expects is that when the viscosity decreases from plus infinity, which in our equation means that gamma increases from 0, some bifurcation should happen. And what we prove is exactly that. We have symmetric solution, but at some point we have a pitchfork bifurcation, a symmetry breaking bifurcation, and we have a pair of new solutions which are not symmetric. This is the actual statement of the theorem. The statement is very standard. I'm not going to read that in detail. Let me just mention that we pinpoint the exact point of the bifurcation, as you see here, at this value of gamma. So this interval is very small, actually. It's written like this because that's the exact value that we have in the computer, but this is a very small interval. And the statement of the theorem is essentially that there is a pitchfork bifurcation at that point. We also have a secondary result, which is the exact shape of the whole branch of solutions. So we have gamma varying from 0 to 2500, and we have the solutions for all values of gamma. We have the explicit form of the solutions for all the values of gamma between 0 and 2500. So this is a secondary result, and the existence of this branch of solution, the actual existence is nothing new. One expects that such solution exists. One doesn't need any kind of computer-assisted proof to prove that. On the other hand, we have the explicit solution for the parameters varying in a very broad range, which is what I would call the computer-assisted interesting part of the result, besides, of course, the actual bifurcation. Also, we proved the existence of the non-symmetric solution, and at some specific value for gamma that you see below, only 2100, 2200, and 2500. We don't have the whole branch. Of course, we could have the whole branch using exactly the same technique, but the non-symmetric branch is much more critical, and it requires a much longer computational time. So we didn't want to do that. So we have the proof of the whole symmetric branch and some non-symmetric solution, plus, of course, the actual bifurcation. And we also have a rigorous estimate for the L2 norm of the gradient, which is important, related to some of the results, some of the pen and paper's results that I will not mention. Now, this is just to give you an idea what the solution looked like. These are at gamma equal to 2500, which means that the viscosity is 1/50. So we see here this symmetric solution and the non-symmetric solution for the same value. Of course, we have the other non-symmetric solution, which is just a reflection of this one. You see that this dynamics is just what one would expect if we had some propeller pushing the fluid to the left at the center of the square. Roughly speaking, this is what one would expect. And also you see that the boundary conditions have the effect that I have described before. The fluid just flows along the boundary of the domain without any friction. Now, this is the only result that I'm going to mention, which is not computer assisted. And we have this result just to point out that the bifurcation does not need to occur when the viscosity decreases to 0. So we have built explicitly a continuous curve of forcings such that even when the viscosity goes to 0, so these forcings are all with L2 norm equal to 1, so we keep the strength of the forcing fixed, and we have the viscosity decrease to 0, and we prove that there is no bifurcation along this branch. So this was just to point out that one expects the bifurcation to occur. We have the bifurcation occur in that particular case, but that's not necessarily so. If the forcing term has a particular shape, this does not need to happen. By the way, we have a conjecture, we have a half proof, but we couldn't complete the proof. We have say a conjecture that we don't need a continuous curve of forcings. We have a specific forcing such that this happens, but that this is just a conjecture. Now, this is the other result. Now we are considering the full equation, meaning that now we have also the derivative with respect to time. And I'm not going to read and comment this theorem, which is, well, a bit tedious. So let me give you the gist of it, which is that at some value of gamma, which is what you see written there, 83 point something, there is a Hopf bifurcation. So in other words, following the branch, at some point, we have a bifurcation where periodic solutions emerge from the stationary solution. This value alpha 0 that you see here, 4.66, and so is the approximate frequency of the solution. Well, not so approximate, because all the digits that you see are rigorous. Anyway, the full statement requires a bunch of definitions, so I'm not going to discuss the actual statement, but what matters is that we have this Hopf bifurcation. And from the point of view of people dealing with Navier-Stokes equation, it is important to note that the value where the Hopf bifurcation occurs is much smaller than the value where the symmetry breaking bifurcation occurs. So this bifurcation occurs with a much higher viscosity than the symmetry breaking bifurcation. It seems that for the study of fluidodynamics, this is an important result. By the way, of course, every result that I'm discussing is very well known in the sense that everybody knows, but everybody knows because there are a lot of numerical simulation that point to these results. At the same time, there is the results on Hopf bifurcations for Navier-Stokes equation are very scarce. The actual results, I mean, proofs of Hopf's bifurcation for the Navier-Stokes equation are very scarce. There are some known examples, but such as the Taylor-Couette dynamics, but to actually see a Hopf bifurcation, to actually prove a Hopf bifurcation for Navier-Stokes equation apparently is not easy. Now, this is a snapshot of the periodic solution. Now, what you may see immediately, so we follow the branch for a little bit up to gamma equal to 84. And these are just two snapshots of the periodic bifurcation. So what you may notice is that they look almost exactly as the stationary solutions that I showed you before. well, these are just snapshots. The actual periodic solution oscillates back and forth between these two dynamics. So this is the way, I don't have a movie to show you, but you may easily guess what happens in the time between these two snapshots. These are the extremal points of this oscillation. It is remarkable in a way that it looks exactly in the same way. It's not the same, these are two snapshots. So what I would like to discuss now is a bit about the proof. In particular, I would like to tell you something about how we prove the whole branch of solution. I think that this is a rather new result to have a whole branch in such a wide parameter interval. Concerning the bifurcation, we also have a slightly new technique. The underlying idea, of course, well, it's a bifurcation. Everybody knows about bifurcation, but we applied a slightly new technique. Okay, and then we will discuss the Hopf bifurcation later. So first of all, the setup is rather standard. I think you have guessed how do we approach the problem. So we consider the eigenfunctions of the Laplacian, of minus Laplacian, with the Navier boundary conditions. So we have the usual sine and cosine. And we write our functions as a linear combination of these eigenfunctions. And we, as usual, I think most of you have done something similar. We denote by this C rho the subspace of L2 of omega, which consists of the function written as this series with the usual norm with a weight rho, which is a number larger than 1. Now, one can easily see that if the forcing term belongs to this space, then any solution is analytic in the closure of omega, by which I mean that the solution can actually be extended to the whole of R2 by symmetry. By the way, this is the reason because we use Navier boundary conditions. One could use either periodic conditions, so periodic conditions are fine, of course, or Navier boundary condition. If we tried to use Dirichlet boundary conditions, but you may easily guess that using Dirichlet boundary condition is much, much harder because of the divergence, the null divergence requirement of Navier-Stokes equation. Anyway, as usual, we write, I was mentioning we have solenoidal functions, so we have to enforce divergence equal to 0. So we define the projection on solenoidal functions, and we write the Navier-Stokes system in a very standard way as a fixed point problem. So we project the equation with the projection on solenoidal functions. Clearly, this solenoidal conditions simply becomes u equal p of u. And then we have the lemma, which states that for a given forcing term f in the space, we can define this operator in C rho, and then the equation 1, that is to say, Navier-Stokes system admits a stationary solution if and only if u is a fixed point of this operator f. So far, everything is completely standard. Yeah, I think that there is nothing really new in this definition. Oh, by the way, you may ask why we use this projection and not, for example, the vorticity. Well, we use the vorticity for the Hopf problem. So the reason because we didn't here is that we were thinking of extending the result to 3D. We never did. Of course, the technique would be exactly the same. The computational time would explode. So we wanted to stay with the actual velocity and not the vorticity because, well, we were planning to expand. When doing the Hopf bifurcation, we didn't even think about it because the problem is computationally much harder. So in that case, we just used the one-dimensional vorticity, but I will talk about that later. Now, the point I would like to discuss, which is what is interesting, I think, the first part, which is particularly interesting for people dealing with computer-assisted proofs is this one. How did we prove the whole branch of stationary solution? Well, first of all, we consider the subspace of the symmetric function, symmetric with respect to the reflection that I mentioned before. We observe that this operator F maps the space of symmetric functions into itself, and also the projection of the function belongs to this space. That is to say, the function is not yet, the projection is in this space. And now what we do is not only we write the possible solution as a linear combination of the basis function that we discussed before, but now we have the coefficients, also the coefficients depending on gamma. And these coefficients, alpha, j, k, which describe I runs from 1 to 2, just the two components of U. J and k are the, say, x and y components. But now we have this dependence on the parameter, and the dependence on the parameter itself is written as a Taylor series, or actually a Taylor polynomial in gamma. So B is the center, delta is the width of the polynomial, and we have this polynomial defined from -1 to 1. By the way, the coefficients with k odd are equal to 0, which simply means that we are in the subspace of symmetric functions. So now we have what we call Fourier-Taylor polynomial. Fourier in x and y, Taylor in the parameter. And remember that the fixed point operator that we have also depends on gamma. So what we are looking for are fixed points of this operator when gamma varies between varies in some interval. Now, the technique of proving that an actual fixed point exists is actually standard. We write the usual sort of Newton operator, this operator n gamma that we see here. This has been rather standard in the recent works by Hans Koch and myself. Anyway, this is just a variation of the standard Newton operator. And then, of course, we apply the usual technique to prove that, I'm not going to discuss that because I assume that you all know about this. We have the usual proof that this operator is a contraction in a small ball, and therefore we have a fixed point. What is interesting here is that the fixed point also concerns the variation in gamma. So we have this gamma that varies in intervals. Which intervals? Well, these intervals. The whole set, the whole interval 0, 2500 is divided in 6 subintervals, and you see here the list of the standards and the width of these subintervals. And just to know what is the size of the computational problem we have, you see also the Taylor order and the Fourier order. Fourier order, of course, means that, for example, for the first interval, we have 10 coefficients in Taylor and 50 times 50 in Fourier. So you see that this is a rather heavy computation. At the same time, you see that, for example, for the first interval, we achieve with a single fixed point an interval of width 500. Then we have to reduce the width 500. I mean, actually, this is the half width. Sorry, I call it width, but it is the half width. So the first interval is between 0 and 500. The second interval is between 500 and 1000, and so on. You see that we reach point 2500. Of course, we also have to make sure that the intervals join at the same point, so that the boundary solution match the boundary interval. The solution at the boundaries of the subintervals actually match. But as I was saying, the interesting part concerning computer-assisted proofs is that this use of this Taylor polynomial to have the whole branch in just 6 steps. We had a previous proof for Kuromoto-Sivashinsky where we had also branches of solution, but those were done small piece by small piece, by interval arithmetics. Here, we decided to use instead this Taylor approach, which turns out to be much faster and also, well, it's also more fun, I would say. Okay, so this is the
Gianni?
standard.
So,
Yes.
So because it's surprising that with only order 10 you can do 500. So what was the rigorous enclosure, like the C0 enclosure that you have along the whole
Size.
Yeah, the rigorous error bound, say the radius of the ball.
Okay, I don't remember the exact number. It's not very small. It's something like okay, I'm not really sure, but it's something like 10 to the minus 3.
Okay.
So it's not very small.
Still, it means that the branch is very kind of almost, I mean, not constant, but it is kind of it's the order 10, but it is not varying a lot over gamma.
Well, you see that the size decreases. With increasing gamma. Yeah, Taylor 10 is not so small after all. Of course, we had to keep. Well, you know well that you can use a higher Taylor order and get a much smaller interval. Of course, this was a sort of I would say a reasonable point to choose. We have the interval sufficiently small, and we have everything.
Okay.
Of course, you can just fine-tune the problem however you want. This is what we did. Okay, this is the standard theorem that I mentioned before that we used to prove the existence of the fixed points. So this is a subinterval and not a cub-interval, but okay, I'm not going to discuss this. So this is the lemma that we have. So this is the lemma that we obtain. And now let me discuss the bifurcation instead. So here we use a similar approach in a way. First of all, how do we set up the bifurcation problem? Well, we just define this new operator f, which is just, so we transform the fixed point equation into the problem of finding a zero of a function. And of course, the starting point is that numerically we see that the derivative of this operator has an eigenvalue 0 for some particular value of gamma. This is the value of gamma that we had. And of course, this leads to the conjecture that there is a bifurcation in a two-dimensional submanifold of the space. So what we do here, we parameterize this two-dimensional submanifold, so this surface, by using the parameter gamma, of course, and some coordinates which will move roughly in the direction of the eigenvector corresponding to the eigenvalue 0. More precisely, we define this two-parameter family of functions by solving the two equations that you see here. L is a one-dimensional projection. As I mentioned, it's approximately, doesn't have to be exactly, it's approximately in the direction of the eigenfunction corresponding to the eigenvalue 0. So you see that we have here corank 1 operator I minus L applied to the function equal to 0, and then we have this one-dimensional operator, well, rank 1 operator L applied to U equal to lambda U. U hat is, again, a function approximately, an approximate eigenfunction of the F. Now, so remember that our purpose is to find the zeros of the function F. Now, assuming that the equation, so equation 10 is the pair of equations that I have just shown to you, assuming that it has a smooth and locally unique solution, then locally the solution that we are looking for, so the zeros of the function f, are obtained by the zero of this function g. So this is just an elementary rewriting of the problem. What we need to show is that, so the function g represents the function f on the two-dimensional submanifold. Zeros of the function g, defined this way, correspond are in one-to-one relationship with the zero of the function f. So this is the strategy. We want to look for this function f. We want to compute this, this function g. We want to compute this function g, or rather compute an approximation of this function g. And then we want to prove that this function g has the structure that leads to a symmetry breaking bifurcation. The strategy, as I mentioned, is similar as before. So we still expand the function u in the eigenfunctions that this is supposed to be an I, not a 1. But we still use the same expansion as before, but now the coefficients depends on two variables. So these are two-dimensional Taylor polynomials. They depend on the variable gamma exactly as before, but they also depend on lambda. And just to give you an idea of the size, these Taylor polynomial are, both these Taylor polynomial are between -1 and 1. So we just normalize the size of the interval 1. And here we have delta very small. So now we are considering very small interval. Delta is 2 to the -11. And also the interval lambda is a small size. It's 2 to the -6. So this is a relatively small representation. But all we need to do is to see that in this small rectangle, there actually is the structure of a symmetry breaking bifurcation. So now what do we do? Well, we prove in the usual way, and again, I'm not going to repeat what is the usual way because it's always essentially always the same, that this pair of equations have a unique solution u that depends on the two parameters in some small around some approximate solution. Again, the function is analytic, and well, what we actually end up computing, what really matters, is that we have a Taylor representation of the function g. This function g, remember, is what matters. Once we have a Taylor representation, of course, with some error bounds on the function g, we can just prove that this function g, remember, this function g is just a Taylor polynomial. So it's very easy to prove that this function g satisfies exactly the assumption leading to symmetry breaking bifurcation. These are the actual statements. This is a very standard lemma. It's actually the same lemma that we use for the Kuromoto-Sivashinsky equation. So the real difference here, and the thing that the thing I think is more interesting to tell you today, is that we checked this hypothesis on the function g. These are all on the first, third, and second derivative of the function g. These are the standard assumptions that lead to the structure of symmetry breaking bifurcation. The novelty here is just that we check this function g by having the explicit form of this function g, or at least a sufficiently rigorous, well, completely rigorous, but sufficiently accurate approximation of this function g as a Taylor polynomial into variables. Now we have, of course, a computer-assisted proof that all these conditions are met. But you see, once you have this Taylor polynomial with rigorous bounds, this part of the proof is completely trivial. Okay, now we have this lemma, as I mentioned, which is proved with the computer, and this concludes the proof of the symmetry breaking bifurcation. Of course, we also check that this set intersects the branch of solutions that we discussed before. So now let me go to the Hopf bifurcation. So here we take a slightly different setting, as I was mentioning before. We compute here this operator that you see denoted by this symbol here. So this is essentially the curl of, well, it's the third component of the curl of the velocity. And so we write the equation in terms of the vorticity phi. So this is the equation that we get. And of course, in the equation, we have the vorticity, but also the velocity. But given the vorticity, we can compute the velocity. We just have to compute this operator here, which is a linear bounded compact operator. So we can just write the equation. This, of course, is very standard. We can write the equation in the vorticity, in the two-dimensional vorticity. So this is the first step that we take. The expansion is almost the same. Now we have a scalar equation, of course, and we have the solenoidal property for free. Now the expansion is in product of signs because we are considering the vorticity. We can easily check that these boundary conditions, so the Dirichlet boundary conditions for the vorticity correspond to Navier boundary condition for the velocity. So we can write the equation like this. And now what I would like to describe is the trick that we chose to obtain the Hopf bifurcation. So first of all, the equation is written like this. In particular, we have this symmetric bilinear form defined in this way. But so far, what we have here is just Navier-Stokes equation in vorticity written in a slightly different way. Just observe that this operator is compact, or at least it is compact with respect to each of the components. So if we look at this as linear operator, if we fix one component, it is compact with respect to the other one. Now we have to expand in time as well. Of course, the expansion in time, we're looking for periodic solution, to pi periodic solution. Remember that we have the period inserted in the alpha parameter. So we just, of course, we just choose an expansion in sine and cosine. So I'm using this function called cosine, which is defined as you see here. And this is just the actual definition that we have in the program. We have a particular object in our programs that gives sine for positive value of n, and cosine for positive value of n, and sine for negative value of n. So this is a way of writing things in an effective and easy way. Now we define the projection onto a subset of n. So the sum on the cosine is over z, because we have to consider both sines and cosines. We don't have any symmetry to exploit to just get rid of sine or cosines. So now what's important here is that we want, the crucial point here is that we want to split the even frequency and the odd frequency. By the way, from now on, when I talk about frequency, I mean in time. So of course we have sort of frequency also in space, but I will call the frequency in space, I will call those wavelengths. Frequency is frequency in time. So what matters here are projection on the even or on the odd frequency part. So we can split any function in the space in the even component plus the odd component. And this will be the crucial step that we're going to take. So what happens close to a Hopf bifurcation? Clearly, close to a Hopf bifurcation, we have non-stationary periodic solution, but clearly they're close to a stationary periodic solution. Well, of course, that's a continuous bifurcation that we are considering. So in particular, the odd part of the solution is going to be very close to zero. So what we do, we change the scale. We do a scaling of the function in this way. We write a new function, small phi, which has an even component and an odd component. The even component is the same of the original phi. The odd component is instead rescaled. So we have a scaling factor acting only on the odd component, again, odd with respect to the frequency of the solution. And the idea is that clearly when you get close to the Hopf bifurcation, the odd component tends to zero. We use this scaling factor in such a way that the even and odd component are of comparable size. Now, this is of course similar to a standard way of approaching Hopf bifurcations. Well, this is just a particular way of having the odd component keeping some non-negligible size. So now we write again the Navier-Stokes equation, but with this new variable phi, which has the odd part rescaled. And as it turns out, the equation can be written as you see here. And you see here that we have this operator Ls. Well, S is just beta squared. Beta, remember, is just the scaling factor. And So we have this quadratic form, which is similar to what we had before, but we have this parameter S here in front of the product of the odd parts. And now we do the usual. We apply the inverse of the differential operator to both sides of the equation, and we get the usual fixed point equation. And you see here that I'm writing the fixed point equation in two steps. First, we have this operator, this delta to the -1/2, the Laplacian -1/2 applied to the LS, and then we have the remaining part. There is a reason because we do that, because the problem is that, of course, we need some normalization condition. In fact, we need two. First of all, we have to get rid of the time invariance of the equation, and we do that by just fixing this component that you see here of the solution to be equal to 0. So this is just an arbitrary choice that gets rid of the time invariance. And then we also fix the value of this other component. So we choose this parameter beta equal to this particular value of this particular component, the component -111, where theta is just a convenient constant that we use in the proof, but doesn't really matter. What matters is that beta is equal to that particular component. So we have this normalization condition. We have this operator A, which just extracts the component 111, which is equal to 0, and B is equal to delta. Now, the point is that instead of course, when you're looking for a periodic solution, you need to have the period as a function of the parameter. Instead, we do this. We choose as parameter beta, more precisely, we choose as parameter beta square, what we call S, and then we compute gamma and alpha. Gamma, remember, is the perturbation parameter, and alpha is the frequency of the solution. So these two values are obtained as a function of this parameter S. It's easy to find those as a function of S because we just apply these operator A and B to the fixed point equation that we had before. Now you see here that we use phi hat, and this is the reason because we had phi hat here. So we split the equations in two because we want this intermediate step phi hat. This phi hat allows us to recover the values of gamma and alpha. And now we do the usual. For the usual means that we define the usual fixed point equation where the value of gamma and the value of alpha is given implicitly by these two relationships that you see here. And now, because of the normalization condition, fixed point of this equation will be non-stationary time periodic solutions. Okay, usual scheme for finding fixed point. Again, I'm not going to discuss this. This is always the same up to small adaptations. And now let's see how we get to the Hopf bifurcation. First of all, we want to pinpoint the bifurcation point. So we want to pinpoint the value of gamma and the value of alpha where the bifurcation actually takes place. So we call these points gamma 0 and alpha 0. And to do that, we consider the projection on the frequency 0, 1, and -1. This is the operator that was defined before. This is just the projection on the frequency -1, 0, and 1. And we look for fixed, we set S equal to 0. S equal to 0 corresponds to the bifurcation point. And we look for fixed point of the function f defined before, the usual function f that leads to a fixed point. This is sort of looking for two eigenvalues for the, okay, it takes time to show, I'm not going to show that, but this is essentially equivalent in looking for the typical condition that leads to a Hopf bifurcation, that is to say, two eigenvalues complex conjugate with 0 real part. We have the usual lemma that says that we actually have the fixed point, and we also, this leads also to the value of the parameter where the Hopf bifurcation, to be proved, Hopf bifurcation happens, 83 point something, and also the frequency or more precisely, the limit of the frequency where the periodic solution is approaches the Hopf bifurcation. So this is the first step. Second step, now we consider the full space, and again, S equal to 0, and again, we prove the existence of, well, actually, no. We consider the same function on the solution that we found before. All we need to prove here is that the derivative is a contraction. We don't actually care in looking for a fixed point. We don't, simply because we already know that we have a fixed point. But here we have the operator, the full operator acting in the full space. Why do we do that? Because if we have a contraction, we can use the implicit function theorem and prove that there exists a solution of the equations for values of S close to 0. So the fact that this is a contraction simply leads to the implicit function theorem, which in turn leads to the existence of a curve S to phi S, which is defined in a disk center at the origin of the complex plane. So we have solutions also, well, also in the complex, also complex value, but of course, as soon as S is real, the solution is also real. Not only that, but we have that this fixed, the solution at S equals 0 coincides to the solution we had before. So this is the periodic solution, and we have automatically the periodic solution that tends to a stationary solution because of the way we built the operator. Then we have the last piece of information, which is the branch of stationary periodic solution. But this is, of course, obtained in a similar way. We have a similar lemma. We have, again, a contraction, but this time we are varying the parameter gamma, keeping both S and alpha equal to 0. We get our branch of periodic solution in a neighborhood of the solution we had before. And then we put everything together. So again, with the implicit function theorem, we have this branch. And then we put everything together. Putting everything together simply means having the branch of periodic solution collapsing to a stationary solution, which in turns belongs to a branch of stationary solution. So this is exactly what we call a Hopf bifurcation. Okay, this is it. These are the papers where these results are discussed. And of course, I skipped a lot of details, and I hope this didn't make things ununderstandable, but this is it. Thank you for listening, and any questions?
Thank you, Gianni, for a very nice talk. So are there any questions?
Yeah.
Mathieu.
I do have a question. And so when you begin your branch, if I recall correctly, you have this U bar for gamma is equal to 0. So how do you get exactly this U bar?
The U bar, what was U bar? Sorry, at which point are you talking about?
Because you prove rigorously your branch of solution for range of gamma.
Yes. So you're talking about stationary solutions.
Yeah, exactly.
Okay, here.
And yeah, I think there's this U bar that you have to begin with.
Okay, so the approximate solution.
Yeah.
How do you get that? Just by just by using this contraction. It has been very easy to find this solution, because I just started from the 0 solution and iterated this operator, and it just converged to a fixed point, approximate fixed point. So it was extremely easy and straightforward.
Okay, so the starting point is the 0 solution.
You see, it's not a problem, because you see, sometimes the problem in finding a solution is that 0 is also a solution, and then any algorithm converges to 0. But here we have a forcing. So 0 is not a solution. So if you just iterate this operator, well, you get immediately the solution you're looking for. So this was really not an issue at all.
Okay, perfect. Thank you.
Oh, I have a question, if I may. Yeah. So first, concerning the symmetry breaking bifurcation. So the reduction to this two-dimensional studies of this function little g reminds me a lot of the Lyapunov-Schmidt reduction.
Yeah, that's exactly what it is.
That's exactly what it is, right?
Yes. That's exactly.
And this function little g is only so the special thing here is that this function little g is an easy polynomial.
Yes. Well, it's not an easy polynomial. We look for an approximation which is a polynomial.
Yes.
Well, it is regular. Given the problem, it is analytic, so we can always approximate something analytic with a polynomial. Nothing more than that.
Yeah. Okay, I understand. Yes.
Of course, we need rigorous bounds on the errors so that we can actually prove the. But yeah, it's just Lyapunov-Schmidt approach.
Okay, so then I'm relieved when this is just Lyapunov-Schmidt. Then my world is in order. So.
Yeah. Yeah, I should have mentioned that. So thank you for
no problem.
Yeah.
I have another question concerning the Hopf bifurcation. So, or maybe a comparison between the two. So you did the symmetry breaking bifurcation for the Navier-Stokes equation, so for the velocity equation, but you did the Hopf bifurcation for the phi function, for the yes. Vorticity. So is this just for fun, or could you have done vice versa?
No, I mentioned this. We started. Of course, these are actually two projects. We started with this idea of the symmetry breaking bifurcation, and we decided to go with the velocity because, well, we said maybe we will move to 3-dimension, and then there is no point in going to the vorticity, which is still 3-dimensional. Well, maybe there is a point, but I'm saying it's not that important. So we started like this. This was just an arbitrary choice. But then when we moved to the Hopf bifurcation, we realized that working with the two components of the velocity was more complicated than necessary. So we just simplified the problem later. We should have done this earlier. I mean,
so you could have done the vorticity formulation also for the symmetry breaking bifurcation, right?
Yeah, it would have been easier, in fact. Just started like that. You start to do something, you start to make a program, and then you don't want to change it. So, but then when working with the Hopf bifurcation, we realized that it would have been much easier. Well, with the Hopf bifurcation, we didn't even think about going 3-dimensional, and then we said, well, okay, let's work with the vorticity, which is easier. Nothing more than that.
Of course, there's another reason for not using the vorticity would be if you are thinking of more complicated domains, like non-simply connected domains, then yes, vorticity is problematic. But that's not what you have in mind.
Actually, having a non-simply connected domain would be really interesting. But of course, you cannot just use these Fourier expansions. And well, maybe your techniques, of course, would apply, but that would be a very different approach.
So maybe, so one of my doctoral students, Jonathan Wunderlich, is doing that. And he will talk next week, I think. Is it next week in this students?
Yeah, we will make the announcement. It's December 3rd.
December 3rd, okay. Yes, then he will talk about these things. And okay, maybe just as an advert.
Okay.
Other questions? I have a question. Oh, Martin, you can go ahead.
So yeah, thank you very much for the talk. It was great. So I had a couple of questions, but one on the stationary problem. So you showed some numbers, so the number of Taylor and Fourier coefficients that you're using. And so at the end of the branch, the matrix you have here actually starting to get really, really big. So do you do anything fancy in the implementation, like to store the approximate inverse or these kind of things, or even to compute it or not?
No, in fact, well, if you're thinking about symmetric solution, which is what is mentioned here, we have half of the coefficients because of the symmetry. Okay. But you can still compute the number of coefficients. It's really huge. And the reason, because we didn't prove, you see, I mentioned that, okay, let me go back. For example, this solution that is shown here has been proved. I mean, this is a picture of a solution which is actually proved. But we did the proof on the non-symmetric branch only at those values of gamma, because with the non-symmetric solution, we need even more Fourier coefficients in order to get a sufficiently accurate result. And of course, the computational time, in theory, there is no abstraction, but the computational times will become really impossible. And that's the reason, because we didn't have the proof of the whole branch here, which is what we actually wanted. But after some time, I had to surrender and say, okay, it was really impossible, too many coefficients.
Okay.
The non-symmetric solution is much worse.
Yeah.
Because it decreases slow, the coefficients decrease slower. So that's much worse.
Okay, thank you. And I mean, maybe I can ask another question, except if someone else is. So yeah, about the Hopf, you said something, maybe it's easy, but I just didn't understand really this thing with splitting the odd and the even component and the.
Yes.
So is it just to simplify your life, or you have to do that really, or?
Well, I don't know if you have to, but that's the way I mean, you have to if you want to do things as we did. The whole point is that, you know, you have a bifurcation, so you need to rescale something in order to actually go to the bifurcation point. Otherwise, you just have the solution collapsing to the stationary solution. And then you cannot use contraction because you don't have it. So this is the scaling that we used.
Okay.
In theory, this is similar to what, for example, JB and his student used for, I think you did the Kuromoto-Sivashinsky, am I correct? I think the underlying idea is, of course, sort of the same. You have to blow up the solution at the bifurcation point. This is just slightly different approach, but
okay.
The basic idea, I think, is essentially the same.
Okay, thanks.
Yeah, it looks a bit similar to what Elena did, right? Yeah. But I have another question, Gianni, if I may. So you get this Hopf bifurcation. So do you know whether that is a supercritical or a subcritical Hopf bifurcation, or you just didn't investigate?
It's supercritical, yes.
And is it part of the proof, or is it just something you know?
No, it's due to the fact that we have beta square. We have the parameter beta square, which leads to that's positive. I mean, so we go to the left.
Okay.
And in fact, besides that, we also have the gamma as a function. Where was it? We have gamma. Forget where this was. Okay, here. We have gamma as a function of the solution, so we actually have it explicit. Okay. We didn't bother computing in it because we don't use it, but so we have it explicit.
Right. Okay, thanks. Any other questions?
Yeah, I have another one.
Okay.
So concerning this, you use the Taylor approximation for the coefficients in this basis representation. And and then you by a bit by surprise, you found that a very small number of intervals of expansion points is sufficient to cover the whole branch. But in principle, you could use anything. There's no need to no enforcement to use the Taylor expansion. You could use any other expansion, right?
Yes.
And so, but my thinking is that the Taylor expansion, in a sense, is not so optimal to cover global approximations, right? Yes, Taylor is very good at one point, but not so good far out. And so, why do you use Taylor and not something like Chebyshev approximation or such?
Yeah, things? Because it is much much simpler to implement. And
okay,
you see, so Chebyshev, I mean, we didn't try Chebyshev. Of course, maybe Chebyshev works better, but still, you see, if you use Chebyshev, the multiplication, we already have Fourier, two-dimensional Fourier expansion. If you have Chebyshev, which is an additional Fourier expansion in a way, well, the multiplication gets slower. Whether it's better or not in the final result, I cannot tell. Maybe it is, but Taylor is simpler and it's simpler to implement and it works. So, well.
These Taylors, I guess you can do order by order. You compute those coefficients order by order and then you bound the tail.
That's not exactly what we do. We just use the contraction. So we have our algorithm that multiplies and that handles this Taylor Fourier polynomials, and then we just let the computer run. You know, our policy is usually let the computer do whatever it can do. So we don't bother. Just contraction leads to the solution. So we don't bother term by term.
Okay. So thank you very much.
Thank
you. Is there another question?
I have just a really quick question. So you computed the branch on this very long interval from 0 to 2500. So was the reason for the cutoff at 2500 because past that point you have a theoretical result?
No. The point is that the bifurcation is at a little higher than 2000. It's what was that, 2065. So we just moved a bit further. Actually, there is another reason, which is purely graphic. We wanted to have the non-symmetric solution to look non-symmetric. So that's the reason, because we went that far. Since we went that far with the non-symmetric branch, then we went that far with the symmetric branch. So that's the actual reason. That's the true reason. We wanted a picture that looked, well, non-symmetric. So you have to go a little farther away. That's it.
All right. That's as good a reason as any. Thanks.
Yeah.
Nice answer, Gianni. Okay. Any more questions? No?
Maybe I have one final one.
Final one.
At least from my point of view, final one.
Final one.
I'm not sure. So you proved it. So I'm considering the time periodic solutions now. So you proved that there is this Hopf bifurcation, which gives you 2 pi periodic solutions in a suitable scaling. And so is there, did you follow these branches further to see if there is a period doubling or further bifurcations, things like that?
I wish. Now, the problem is that here the number of coefficients is huge. The fact is that we chose these Navier conditions. We had a reason. I'm not going to discuss this reason. It would take forever. There's a reason because we chose this particular boundary condition instead of, for example, periodic boundary conditions. And by doing so, the actual solution requires a lot of coefficients. So the picture that I showed you here, so these 2 snapshots are purely numeric. We couldn't prove the solution here. I mean, in principle, we could, of course, but the computations are too heavy. We need a lot of coefficients, both in time and in space. We needed something like 300 coefficients in time, so a Fourier polynomial of degree 300, which is actually 600 because we have 300 sine and 300 cosines, and then something like 100 or so times 100 coefficients in space. So you see that the size of just of the matrix of coefficients is huge. So we couldn't follow. We wish we could, but we need some refinement of the technique to get to that.
Or higher computer power.
Or more computer power, more memory. It's also an issue of memory here. Yeah. Because we have everything running in parallel. We had 40 tasks running in parallel, and we also need a lot of memory to run 40. So yeah, it's really complicated. Oh, I mean, it's not complicated. It's challenging, technically challenging.
All right, thanks.
Okay. Let's first thank Gianni again for his very nice talk.
Thank you.